All right, welcome back. We're going to talk about our we're going to start our second linear algebra review session. Today is focusing on solving ax equals b. So put this in context, last time we talked about geometry and vectors and hyperplanes and also the row and column stories of matrices. We're going to be seeing a bunch of that again today, but focusing on actually solving linear systems. As a quick overview, next time we're going to be talking about spectral solutions for spectral properties of matrices. That's going to be on Friday, same place, 7 o'clock right here. And that will be the third one, so third and last one. OK, so last time, what was the equation of the entire last time? Well, if there was one equation that kept coming back to haunt us, I think it was probably this guy, n transpose x equals b. Right, and let's just remind ourselves what this means. What was n? What can we interpret n as? A normal vector, right? A normal vector to some hyperplane. And b, what sort of meaning does b have? Right, basically, where are we shifting that hyperplane in space? So n is telling us the orientation of that hyperplane, and b is telling us where that hyperplane exists in space. So when we finished yesterday, last time, we started talking about systems of hyperplanes that might look like this. Right? And what am I saying if I give you a set of simultaneous hyperplanes? I'm saying find the intersection of those hyperplanes. So if I started off in a 37-dimensional world and I hand you one hyperplane, what dimensionality am I going to be able to find? Let me say this another way. X is the set of all vectors that is perpendicular to n. Right? What dimensionality is x? n minus 1, or 36 dimensional. And then I add another hyperplane and I lock down one more degree freedom and I'm 35 dimensional, 34, 33, 32, 31, and so on and so on and so on. Right? Everybody remember what we're talking about? So if this is one of our hyperplanes, this is one of our vectors, the solution to this first equation is the set of all vectors which are perpendicular to n1. If I add in another normal vector, let's say this one, that's going to give me another hyperplane, which looks something like that. And again, all the vectors in this hyperplane are perpendicular to n2. And when I'm taking these equations simultaneously, of course, x has to be a member of both of these hyperplanes, has to be the intersection, so we're going to end up with a solution that looks like this. Right? The line that goes through both of those hyperplanes. All right, and then basically we said that we could convert this into an ax equals b problem. How do I do that? Well, I'm basically going to take a matrix of the n's, n1 transpose, n2 transpose, x equals b1, b2. All right. And that's pretty much where we left it last time. Everybody on board? Thumbs? Fantastic. So today we're going to talk about solving this a little bit more. The first method that we're going to talk about is Gaussian elimination. So this is kind of your go-to, I just took a linear algebra course, boy do I know how to do Gaussian elimination. So let's try a simple example. 1, 3, 2, 8, x, y equals 2 minus 6. So let's ask ourselves first a little question. Do we think this guy has a solution? Yeah, it looks pretty good. Right? What test are you doing in your head when I ask you that? Right? Is this one a multiple of this guy? Right? Or are these hyperplanes, or are these normal vectors, if these two normal vectors pointed in the same direction, then their hyperplanes would be degenerate, right? And that would be a problem. Another way of viewing that is that if these guys were multiples of each other, that's sort of the, I'm sorry, let me back up. If these normals point in the same direction, then their hyperplanes overlap, and then there may not be a solution. That's sort of the row story that we talked about last time. The column story, if this was a multiple of this guy, then basically I have two of the same ingredients, right? I've got milkshakes and I've got milkshakes. And the only thing I can form with milkshake and milkshake are other milkshakes. I may not be able to get my recommended daily allowance. Those of you who were not here last time are probably thoroughly confused by that example. The short version is that milkshakes are delicious, and that's all we need to know. Okay, so here's our equation. We look at these guys. They look like they're independent. So how do we proceed? What's the way that we learned how to solve this system when we were in 9th grade, Algebra 1? Yeah?
I mean, you could say take the top row, I think, multiply it by something, and like -2, and add together.
Right. So we learned this set of transformations that are legal. Right? We can take any row, multiply it by anything, and add it to any other row. Right? And in doing that, we have sort of a strategy. What do we want to do? Yeah, what we'd like to do is to end up with a simple expression for y. And we can get a simple expression for y by making this guy go to 0. Because if this guy is 0, then we're going to have 0x plus 8y equals -6. Right? And I know how to solve that. That's easy. So how do I make this guy turn into a 0? Well, I'm going to add some multiple of this row to it. I think your suggestion was -2. Right, so if I multiply the top row by -2, that gives me the row -2 minus 6 minus 4. And now I can add this row to this row, and I'm now going to end up with the system. This turns into a 0. This guy turns into a 2. This guy turns into a -10. Everybody on board? All right. So now, what could I do? Well, one thing I could do is I could solve for y now. Y is going to be -5. And then knowing the value of y, I could go in and plug in up above and turn this guy into a simpler expression involving only x. Another thing I could do is that I could try to reduce this guy. So this form here is called echelon form, because we've got zeros below the diagonal. We could also go to reduced echelon form, which is where I make everything off the diagonal zeros. Now, that's the sort of simple version. How would I do that? What if I wanted to put this into reduced echelon form? Everything off the diagonal needs to be 0. I need to make this 3 go to 0. Right? The only thing I can really do is to multiply this row by something and add it to this guy. A suggestion? -3/2, right? Okay, so let's write this row out times 3/2, -3/2. So this is going to be -3 minus 30 plus 30 over 2 is 15. Did I do that right? Now I add this row to this row. And now I'm going to get a 0 here and a 17. I think something went wrong here. I don't think that was my answer. What did I do wrong? I shouldn't have erased my previous work, because now it's a little hard to reconstruct this. Let's see. I had 1, 3, and 2. Right? And I wanted to make this -3/2. All right, so I'm multiplying this row by 3/2. 0 minus 3. 3/2 is -15. That's right. 0. All right, this turns into 0. This turns into 17.
It is right. Yeah, it is right.
Okay. I have a mysterious phantom solution in my notes here. That's exciting. Okay. Well, at this point, we're home free, right? We can just read off y is 5 and x is apparently 8.5. Whatever. What's that? X is 17. Oh, yeah, woo, it's 7 o'clock. The important thing is that we know what we're doing, not that we get the right answer. All right. So that's Gaussian elimination. Basic idea here is that we converted this into reduced row echelon form. Now, if I wanted to come along and solve the same matrix again, 1, 3, 2, 8, This is the matrix we had before. And I gave you a different B. 106 minus 220, 217. Right. I'd basically have to repeat that process again. Right? It'd be a fair amount of work. So one question you might ask yourself is, can we do all that work front-loaded? Suppose I needed to be able to solve this system over and over and over again. Right? So going back to our example from last time, maybe I've still got my menu from Arby's with chocolate shakes and French fries and all the things that I'd like to eat, but every single person might have a different recommended daily allowance. Now I want to be really efficient at computing how many milkshakes and how many hamburgers and how many French fries everybody should eat. Right? Rather than repeating the Gaussian elimination for every single person that walks in, could I make that operation go a little bit faster? The answer is yes. So what we're going to do is, instead of solving this problem, let's solve a slightly different problem. 1328 x equals 10. Right? Let's basically figure out if someone came in and how many of you remember the example from last time? Should I just stop using it? The milkshake example? Okay, I'm going to continue using it. The basic idea was that we have a bunch of ingredients, a bunch of food that we can eat. Each one has some number of calories, some amount of fat, and some amount of protein. And then we've got a recommended daily allowance telling us how much we are supposed to eat every day in terms of calories, protein, and fat. And the idea was, can we solve for how many milkshakes, how many hamburgers, and how many French fries we need to eat so that we get the right amount of food, so we get the right amount of calories. And so hopefully everybody's sort of on the same page. So let's consider, this is sort of simple version. This is like our milkshake, and this is sort of our French fries. And what I could say first is, let's just try to figure out if someone needed one more unit of calories, how would I give it to them? Right? So I solve this system. We use the same methods that we used before, and I'm going to end up with x equals 4 minus 1. Right? So now if someone comes in the door, and all they need is 100 calories, what do I tell them to eat? 400 milkshakes and minus 100 French fries. Right? Here's milkshakes, French fries. Everybody see what I did? Now I could also ask a different question. I could say, what if someone comes in and all they need is one more unit of fat? What do I tell them to eat? So I can do Gaussian elimination again and solve this system. And in this case, I'm going to end up with x equals minus 1.5 and 0.5. And you can see the breakdown here. Sometimes we're going to get solutions that say someone should eat negative milkshakes, negative numbers of milkshakes, or negative amount of French fries. We're going to assume that's OK. All right, so now someone comes in and they say, I need 100 calories and I need 10 grams of fat. So how do I tell them what to eat? Right? 100 times this plus 10 times this. Does that make sense? So somehow, these two vectors here make solving this system really easy. Does anybody guess where I'm going with this? Well, so let's write down both of these constraints at the same time. So the first time we solved it for 1, 0, and the second time we solved it for 0, 1. So we could actually solve both of those systems at the same time. Right? There's no reason that b needs to be a vector in our ax equals b problem. Right? X and b could actually be matrices. That's totally fine. And what that amounts to is repeatedly solving the system for every column of b. So let's see what I mean. Here's 1, 3, 2, 8, our matrix from before. And let's first solve it for 1, 0, which we just did. We know this is going to be the answer. And then let's solve it for this guy, like this. And now our x matrix is going to be this followed by this. 4 minus 1 minus 1.5, 0.5. Comments? Right. Right. What did we just do? We just computed the inverse of A. Right. Computing the inverse of A is repeatedly solving AX equals B for all the simple unit vectors. Everybody see this? This is A inverse, and this is I. That's pretty cool, right? Now, actually, I think inverses are really cool. So if you think about the properties of a matrix inverse, it's got a lot going on. So let's think about this more abstractly. Pretend this went up. Here's a matrix. Let's call it matrix A. It's a nice and square matrix. And here is A inverse. And of course, we know that if we multiply these guys together, we're going to end up with the identity matrix. Now, what this means, we can interpret this on a sort of column by column basis of A inverse. So let's consider the first column of A inverse. And of course, A has a number of rows. What do we know about these dot products? Well, the first thing we know is that those dot products are right here. Right? This dot product is this entry of the identity matrix. This dot product is right here. This dot product is here. And this dot product is here. Right? That's just matrix multiplication, nothing earth-shattering right now. But because this is 1, 0, 0, 0, we actually have something kind of interesting going on. This first column of A is a vector which correlates with only one of the vectors, the row vectors of A. Right? This column vector of A inverse only correlates with this guy. You multiply it by this guy, you get nada. It's perpendicular. This guy and this guy, perpendicular. This guy and this guy, perpendicular. That's pretty cool. So what is A inverse? A inverse is a collection of column vectors where each one correlates with exactly one of the rows of A. It's kind of a neat way of thinking about that geometrically. Now, what does that buy us? Well, one thing is it allows us to rapidly compute what kinds of junk food people need to eat. That's a joke. Thank you. I don't need your pity. I'll take your pity. The other thing, so what else could this do? Well, you could imagine a simple sort of classifier system, sort of a machine learning type of classifier, where you've got vectors that describe features of animals. Right? So one thing you might have in this feature vector might consist of things like, are they a mammal? How much do they weigh? Do they have fur? Do they have hair? I don't know. Imagine some really high dimensionality space. Right? Do they give birth live or do they have eggs? So every animal you can imagine describing in terms of one of these feature vectors. And you can imagine that in some very high dimensional space, in this case high meaning 3, cats are over here. And ducks are over here. And dogs are probably sort of nearby cats, right? Because dogs are both mammals, they both are hairy, and they both make messes in your house. So one thing that you might do, having collected this information about here's in feature space where the perfect cat is and where the perfect dog is, now someone comes along and says, I got this critter, here's its feature vector, what is it? Right? And so you come along and you get this query point, let's say it's here, Q for query point. And what you want to do is you want to ask something about, is it a cat or is it a dog? Or is it a duck? So one thing you could do is you could just take those points in space and say, which point is Q closest to? Yeah, you could do that. But another thing you could do would be to try to figure out which animal is it most similar to. So here's the issue. If I considered cats and dogs as sort of vectors in space, one thing I could do is I could compute the dot product with Q on top of each of these guys. Right? How similar is Q to a cat? How similar is Q to a dog? Now, one thing that's kind of annoying is that Q is going to have a pretty high correlation with both dogs and cats. It's not going to correlate very well with ducks because it's way over here. So one thing you might ask is, could I come up with a different set of tests, a different set of vectors to test against, where if it's a cat, it's going to have a maximal response in the cat direction. If it's a dog, it's going to come out as a unit vector in the dog direction. Is there some transformation space where I can project a point in feature space into animal space? Right? So the ideal case is if I imagine a vector, some matrix here, and I put in the feature vector for a dog, what I want out is, let's say, here's cat, the cat indicator. Well, it's not a cat. Here's the dog indicator. Well, it is a dog. And here's the duck indicator. It's not a duck. Right? It'd be nice to be able to find some coordinate transformation such that if I put in my coordinates for dog, multiply it by this thing, I basically get the answer just staring right back at me. It's a dog, darn it, because the dog indicator is 1. So what matrix is this that projects our data into this indicator space? Right, it's the inverse of the feature of the matrix formed by the feature vectors for cats, dogs, and ducks. That's kind of cool. I don't know if that's useful, but it's kind of cool. Okay. So let's consider some different ways of solving AX equals B. So Gaussian elimination is sort of the beginner method. We're going to consider another method called LU decomposition. Let's start off with an example, this time in 3D. 1, 1, 3, minus 2, 1, 1, 1, minus 2, minus 5. X equals 4 minus 4 minus 1. All right, so LU decomposition is sort of thinking about the lesson that we learned from Gaussian elimination and trying to move forward with it. Right? Gaussian elimination, the basic idea was let's try to make Gaussian elimination. Gaussian elimination makes that matrix triangular. Right? There's something good about triangular matrices. LU decomposition tries to do the same thing. We're going to try to factor this matrix into some triangular forms that are going to be that make it easier to solve the problem. So what we're going to first start off is with an assertion that any matrix can be factored into LU. What does LU stand for? LU stands for lower triangular, U upper triangular. So this matrix here can be written as the product of a lower triangular matrix. So it's going to have some zeros in the upper right, and an upper triangular matrix. Ooh, I need a blank here as well. That's sort of the definition of a LU decomposition. Let's scratch our heads. Is it first plausible that such a factorization exists? Well, so one sort of sanity check you could ask yourself is how many degrees of freedom do we have? Right? So how many numbers are there in this matrix? 9. Right? What if I told you there was a factorization for any matrix that required only 3 numbers? Right? You'd say no, no. So how many numbers are there in this LU factorization? 12? Right? 6 here and 6 here. Right? And so I've got 12 degrees of freedom down here to work with to be equivalent to a matrix with 9 numbers. That is not a proof, but it's sort of a comforting thing, right? Because at least 12 is bigger than 9. There's some reason to hope that it might work out. So let's give it a shot. So how do we go about doing this? Oh, well, one more thought is that because there are 12 numbers, which is more than 9, what we might suspect is that there's might be multiple ways of factoring it. Right? I have more flexibility with this factorization than I have in this matrix because I have 12 degrees of freedom versus 9 degrees of freedom. And we're going to see that in a moment. So how might we go about factoring this matrix using an LU decomposition? Well, it's actually a really simple approach. What I don't want to do is write down an algorithm, sort of an algorithmic block, step 1, do this, because I look at that code and it's hard to understand. It involves lots of dot products and subtracting things and blah, 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 blah. But if you are lazy like me, it's actually really easy. So all you're going to do, let me just copy this matrix here. Minus 2, 1, 1, 1, minus 2, minus 5. All you're going to do is look for elements for entries of this matrix that are easy to compute over here. Right? Ones that I get mostly zeros or no numbers. So a bad choice would be to try to make this product equal minus 5, because there's 6 unknowns involved in that. Right? I have no idea where to start. What's the alternative? Start in this upper corner, right? In which case I'm going to have this times this, plus this times this, plus this times this. Right? Those zeros are saving me. Right? The only thing I have left is, let's call this A, and let's call this M. Right? This product needs to be 1. A times M equals 1. Now, we can already see that we've got some choices. There's a bunch of numbers that we can multiply together to get 1. And so here's how we're going to resolve that. We're going to get rid of 3 of our degrees of freedom here by constraining these guys, the diagonal of the L component, to be 1. So now I've just got M plus 0 equals 1. What should M be? 1, thank you. All right, let's continue our habit of being lazy. Any suggestions? What's the next one that we could compute? What's a dot product that we can evaluate over on this side between some row and some column that only has 1 unknown in it? Yeah, I think I'm hearing 2 comma 1, which is this dot product. 1 times something plus 0 is minus 2. Minus 2. All right, here's what I want you to do. I want you to finish factorizing this using LU decomposition. Right? Again, the key idea is you find a dot product over here that only has 1 unknown in it, and you set it equal to the corresponding element over here. So just as one more hint, what would be another good one to do next? What about this guy? That one would work. Go ahead, grind that sucker out. All right, I'm seeing more and more heads poking up now. Who's got it? Give me a thumbs up. Oh, I'll give you another 30 seconds or so. All right. Okay, who's got it? Thumbs? Great. So let's go ahead and can someone tell me what they got here? 1 minus 1, good. 1, 3, 3, 7, minus 1. Great. So if you guys didn't get that, this would be a good thing to be able to do, because actually, you might find yourself on a desert island someday in need of computing an LU factorization. Could totally happen. Okay, so here we are. We've gone through this process of factoring A into L times U. That's great, but what does that actually buy us? Our goal, after all, was to solve AX equals B. So here we are. We just factored A as LU x equals B. Now, I'm going to switch to drawing these matrices. Here is L. Here is U x equals B. All right. So what we're going to do is a little trick. We're going to do a change of variables here, and we're going to let y equal ux. Right? Y. What kind of linear algebra entity is y? Matrix, vector. It's a vector, right? U times x is going to be a vector. So let's do this. Times y equals b. Is that an easy system to solve or a hard system to solve? Easy, right? It's kind of like it's a triangular system. Now, unlike Gaussian elimination, it's sort of an upside down triangle, right? We usually make it upper right triangular when we do Gaussian elimination, but it's still easy, right? What element would you solve first for in y? The top one or the bottom one? The top one, right? It's the same trick we did in LU, right? We're lazy about it. We try to find some unknown element in y that only has one unknown involved in it, right? So if we consider this dot product, right, it's only got one unknown in it. So this times this has to be equal to the first entry of B, right? Oops, that's not what I meant to draw. Everybody on board? And now, having solved for the first component of y, what do we do next? We solve for the second component, right? And now we know this column, this entry here, so we can perform that multiplication. We're going to end up with the second element of y times times this guy equals the second element of this, right? Basically, anytime you've got a triangular form, you can sort of unzip the solution, right? You start at the tiny end of the triangle. It gives you one variable. You use that to solve the next most complicated one. Down and down and down you go down the triangle. Everybody on board? Great. So we do this, and we solve for y. That's not what we want, though. What should we do next? Well, we've got this equation here. Let me write it the other way for those of you who are still scratching your head. What does that look like? Looks like an AX equals B problem, right? Because we just solved for y. We know this. We know u. Now the only thing we don't know is x. What about u? Well, u is upper triangular. Is this an easy system to solve or a hard system to solve? Easy, right? It's a triangular system. This time we're going to start from the bottom. Everybody on board? Okay, so I'm not going to have you actually solve this system here because there's a fair amount of just number crunching and back substitution. But I encourage you to go home and work this out and make sure that you've got it down. So if you get used to this sort of, and remember, my strategy here is not to memorize the algorithm, but to just remember to be lazy. Right? Just look for the thing that you can solve. Remember the general strategy of factoring things into the triangles, and then just be lazy about it. Try to figure out what you can do next, knowing what you know now. And then the algorithm is obvious. It's obvious what to do. Okay. For our next experiment, let's consider this system. 2, 0, 2, 1, 0, 2, x equals 4, minus 1, minus 1. All right, you look at it, what's your first reaction? It's over-constrained, right? And when we say over-constrained, what are we really saying? What's a consequence of being over-constrained? Right, there's not going to be an exact solution. Right, under what conditions would there be an exact solution? Right, where if one of these was some linear combination of the other two. Right, in that case, then this would have an exact solution. In this case, it doesn't. So what are we going to do? Well, one thing you might say is, well, let's try to solve the system as best we can. So in order to solve the system as best we can, we need a notion of an error metric. So what's a natural notion of error? Let's call this A, x equals b, as usual. So if I give you an x, and you're a magic box, and I say, here's an x, how good is it? What would you compute? Ax minus b, or b minus ax, right? What you'd want to say is, I know that what I want to have happen is that ax is going to be equal to b. So let's compare how close ax is to b. So let's define an error term that is e is ax minus b. All right, so now this is easy, right? We just minimize e and off we go. What's the problem? What kind of linear algebra entity is E? It's a vector, right? Because it's the difference between two vectors. So I'm not sure what it means to minimize a vector, right? How do the elements count with respect to each other? Do we count the first one more than the second one? I don't know. So what could we do? I like it, right? So let's try to minimize the length of the E vector. Okay, so what's the length of the E vector? Something like that, right? Right, where you add up the sum of each element and you take the square root. Right? But taking the square root, if those of you who've done some optimization before, that's kind of an ugly thing to have lying around. One thing we could try solving instead would be the squared magnitude of E. Now, I'm going to assert that if I minimize the square of the magnitude of E, then I'm going to get the same solution that if I minimize the length of E. Who believes that? Great, right? Why is that? Right, E squared monotonically increases with increasing E. Right, so there's no sort of funny little loops where E squared suddenly goes down. Right. Was there a question over here? I heard something. All right, so let's minimize this. What's another way of writing the squared magnitude of a vector? E transpose E. All right, and now this thing is what kind of linear algebra entity? A scalar. All right, now I'm happy, right? I know how to minimize or maximize a scalar. Right, what's the sort of calculus 1 story for how to minimize some function? Right, we're going to differentiate it with respect to the parameter that we control, which in this case is x. Right, x is the thing that we get to choose. We're trying to minimize E by picking an x. So, and you notice that E is really a function of x. Right, so what we're going to do is we're going to take the derivative of this with respect to the x. What's the next step? Set it to 0, solve for x. Piece of cake. So let's do that. Here's E transpose E. Let's write it out just for giggles. AXB transpose AXB. Right, everybody see what I did? Here's E. I just plugged it in. Right, now, I need to multiply this sucker out. being very careful about the fact that now we're talking linear algebra, not plain old arithmetic, so I need to be careful about transposes and making sure that I don't need incorrectly change the order of multiplications. So what do I do? Well, the first issue maybe is this transpose here. Right? It might be nice if I could push this transpose inside. So let's do that. Everybody happy with that? Right, can I distribute transpose like that? Okay, so now I'm almost home, right? I just do A transpose, X transpose minus B transpose, right? No. Right, what did I do wrong? Right, when you take the transpose of a product, you need to switch the order when you take the transpose. So this is going to be X transpose A transpose minus B transpose. All right, now we're in great shape. Now we just multiply these guys out. And remember that we can't change the order of things, right? So when I multiply this guy out, it's got to be X transpose A transpose on the left and AX on the right. Right? I can't get clever or lazy and start switching things around. So the first term, X transpose AX. What's the next term? Maybe this guy times this guy, which is X transpose A transpose B times maybe this guy, minus B transpose AX plus B transpose B. How many of you are 100% comfortable so far? Great. And we already said that this is a scalar, right? What's the transpose of 4? 4, right? So the transpose of a scalar is the same scalar again. So one thing we could ask ourselves, are any of these terms here transposes of each other? The middle two terms, right? Right, this guy is a transpose of this guy. If I switch the order of these guys and took the transpose of each individual one, right, I'm going to get B transpose AX. So what does that allow me to do? Allows me to write, just copying this term over, minus 2 X transpose ATB plus BTB. Now we are cooking. All right, so this, we haven't actually even gotten to first step of our Calculus 1 strategy here. Step 1 was to take the derivative. So we want to take the derivative of this expression with respect to x. Now, how many of you know how to take the derivative of an equation that involves matrices? I see one person. That's less than 70. So let's go into it. So the main thing to keep in mind is that there's really no magic involved. Remember, these are all scalars. Right? So if I multiplied all this out, this would just be equivalent to some big polynomial. Some big polynomial in x and the various components of x. The other thing to keep in mind is that when we do take derivatives of equations that involve matrices, it's a whole lot like taking derivatives of equations on ordinary scalars. It's going to have the same sort of feeling. There'd just be a couple little tweaks to account for the fact that we can't move terms around and we have to keep our transposes in the right place. So let's try a very simple example. Let's try taking the derivative of 4, 3, 3, 2, that's a bad matrix. 5, 3, 3, 2. I like positive semi-definite matrices, and the first one wasn't. Okay, so here we have this. Here's our A, and we have this guy. Here's our x. So what is the partial derivative? Oh, so first thing is that there isn't an x. X is actually a bunch of variables, x1 and x2. So when I say take the derivative with respect to the vector x, what I really mean is let's take the derivative with respect to x1 and x2, the partial derivatives. All right, so let's take the partial derivative of this guy with respect to the x vector. All right, so what does this mean, first of all? Let's go back to the equation story. This is just a set of two simultaneous equations, a set of two simultaneous hyperplanes, if you like. Right? 5x1 plus 3x2, 3x1 plus 2x2, right, simultaneously. Do we know how to compute the partial derivatives of that with respect to x1 and x2? Sure. So let's do it. What is the Jacobian of this set of equations with respect to x? Now, Jacobian is just fancy math speak for I want to sound smarter. No, it's fancy math speak for a matrix of partial derivatives. So here's our Jacobian. So the way to think about this is we've got our equations running this way and our variables running this way. Right, so here in the first column are going to be all of our partial derivatives with respect to x1. In the second column are going to be all the partial derivatives with respect to x2. The first row is going to be all the partial derivatives for this equation. And the second row is going to be all the partial derivatives for this equation. OK, so what goes here? The partial derivative of the first equation with respect to x1, which is, everybody? 5. What goes here? The partial derivative of the first equation with respect to x2, 3. How about here? Partial derivative of the second equation with respect to x1, which is 3. And here, partial derivative of the second equation with respect to x2, which is 2. Well, look at that. What is the Jacobian? It's a. Now, is that so surprising? What's the derivative of 4x with respect to x? 4. Right? So just like in the scalar case, that constant coefficient just hung around. Right? So the partial derivative of ax is a. Easy, right? All right, so that tells us how to handle some of these terms. B here we're not too worried about because b is just a constant, but it doesn't tell us how to handle this guy. This is really a quadratic term. So how do we compute the partial derivative of that? First of all, we're going to need some more whiteboard. Five, 3, 3, 2, x1, x2, x1, x2. Right? This is x transpose ax, which is a scalar, right? And so it's equivalent to a polynomial. Specifically, what polynomial? You guys can all do this in your head, or do you want to work it out? Let's work it out. Let's do the right side multiplication first, and then we'll do the multiplication by the left-hand side. So when I multiply this guy times this guy, I'm going to end up with what kind of linear algebra entity? It's a 2 by 2 matrix by a 2 by 1 column vector. I'm going to end up with a column vector, dimensions 2 by 1, right? So 5x1 plus 3x2. 5x1 plus 3x2. And 3x1 plus 2x2. All right, and I've still got my x1, x2 here. All right, this is a 1 by 2 times a 2 by 1. It's going to give me a 1 by 1, which is a good thing because I was expecting to end up with a scalar. So 5x1 squared plus 3x1 x2, that's this product, plus this guy, 3x1 x2 plus 2x2 squared. Everybody happy? Right, key thing to remember here is that at the end of the day, this is just a polynomial that we can manipulate. Now, I'm going to do the same thing. I'm going to take the partial derivative of this polynomial with respect to the x vector. Now, when x is a vector, what I really mean is I want the Jacobian. I want the matrix of partial derivatives. What are the dimensions of that going to be, of that Jacobian going to be? 1 by 2. Why 1 by 2? Right, I've got one equation. That tells me how many rows there are going to be, and still two variables, which tells me how many columns there are going to be. So here's my Jacobian. It looks like this. What's the partial derivative of this guy with respect to I totally lost my train of thought. Partial derivative of this guy with respect to 5. With respect to x1. Well, so it's going to be 2x1, 10. Wow, boy. 10x1 plus 6x2 plus 0, right? Because this guy doesn't have anything. What's going on over, do the same thing, repeating it with x2, taking the partial derivatives with respect to x2. So I'm going to have a 3x1 plus a 3x1, which is a 6x1 plus 4x2. All right. Yes, it is. Yes, it is. Thank you. Now I have to do it again. 6x1 plus 4x2. Okay. All right. Are we ready to go now? What do we do next? Any thoughts? Well, at this point, we've got kind of a hard thing to look at, right? There's some structure in here. We can see our original numbers from this matrix in here, still in here. But maybe it's a little bit hard to work from here into back to a nice linear algebra form. So what we could do instead was we could guess what the answer is going to be and see if we get back to here. Right? So if I had, in scalar case, ax squared, what would the derivative be? 2ax. Well, maybe that's what we end up with here. So let's try that. 2ax. So what would 2ax be? Well, that would be 2 times 5x1 plus 3x2, 5x1 plus 3x2, and 3x1 plus 2x2, 3x1 plus 2x2. All right, are we happier now? Anybody seeing anything? Right, these are transposes of each other. Now, was I supposed to end up with transposes of each other? I don't think I was. I think I screwed up somewhere. Say it again. I heard something. Was someone? I can't hear you. Figure this is the one I've done so many times I didn't put in my notes. So now I'm standing in front of the whiteboard where I feel stupid. So where did I make a mistake? So somehow these were supposed to end up being the same. So somewhere we made a mistake. Let's see. We started here, then we multiplied it out, and we ended up with a scalar. That's good. Then we took the partial derivatives of this with respect to x1 and x2. It's one equation. That we did right. So this should be like this.
Did you try to choose a matrix of
I'm not sure I understand. I don't think we need to flip those around. All right. You know what? Let me just chug ahead a little bit, and I think it's going to be, we'll leave these here, and then I'm going to move to the next part of this derivation, and I suspect along the way I'll figure out what I did. There's just something silly I did. All right, so here we were, back here, and now we're going to take the partial derivatives of this. We've got x transpose ax. So we can treat this guy as one of these quadratic forms. This marker doesn't work. So that we've got x transpose times some matrix. So what we're expecting is to end up with a form of 2, this thing, x. So as we take the partial derivative of this guy, partial derivative of E transpose E with respect to x is equal to 2 A transpose AX. What's the partial derivative of this guy? So we know that there's, the only thing I screwed up in here is somewhere I lost a transpose. Right? I don't know where the transpose went. Does everybody see? They're equivalent to each other except for a transpose. So somewhere in there I lost a transpose. I don't know where it went. All right, so we do the same thing here. We're now taking the partial derivative of this term with respect to x. What are we going to end up with? It's like what we did before, right? What's the partial, I don't know where it went. What's the partial derivative of 4x? What's the derivative of 4x with respect to x? 4. Right, so what I'm expecting it to be is 2A transpose B. And that's actually what we worked out on our previous example. Right, minus 2A transpose B. What's the partial derivative of this with respect to x? 0. That one's nice and easy. All right, great. So now we're in good shape. For those of you who are angstful over this, I can email out a correction. I just don't know where the darn transpose went. All right, so now we've taken the partial derivative, and we're going to set it to 0. Yes?
Why did it x transpose ax? There's no x transpose ax term in the equation.
Which one?
You took x transpose ax and found it derivation.
I'm sorry, I just can't quite hear you.
X transpose ax, you took the derivation of x transpose ax by the top.
X transpose AX.
But I don't see that term anywhere in the equation.
Oh, it's analogous to this one. Right, in this case, it was still it's still a square matrix, although it's A transpose A. Right, I just meant A to represent a generic matrix. In this case, the generic matrix is our A transpose A. Yeah?
Yeah, the 2 times A transpose A is actually the general A there, A plus A transpose.
Ah, right, so 2AX, but what I actually have over here is 2X transpose A transpose. Thank you very much. Chocolate bar for Jen? Thank you. There was my missing transpose. Did everybody hear that? Right, so when I did the math up here, I was talking about a generic A, not our A. Right, and when in the equation that we actually have, we have A transpose, not A. Thank you very much. Whew. All right. So now we've taken the partial derivative. We want to maximize the expression. What's the next thing for us to do? Calc 1. We set it to 0 and solve. All right, so now we do a little bit of linear algebra. We can cancel the 2's. We get A transpose AX equals A transpose B. Well, that's lovely. What are the dimensions of A transpose A? For this A. A transpose A. 2 by 2. Right? A transpose is going to be out in front. It's going to look like this. I'm going to have a 2 by 3 multiplied by a 3 by 2. I'm going to have a 2 by 2 matrix. This 2 by 2 matrix is going to be invertible. So in fact, I'll be able to solve this system. Right? This is now a AX equals B problem. Right? Here's my, I've got a lot of A's on the board today. Wowzers. But now I could solve this problem. Now, where did all this come from? Let's recap. we started off with an overdetermined system. We know that there's no solution, no exact solution in general. What we decided was that we were going to define an error metric which was equal to how close did we get. And we're going to minimize the length of that error metric. So we wrote down the error metric, we expanded it out, there were some shenanigans involving me losing some transposes, but at the end of the day, a little bit of calc later, we're able to show that this is our solution. Right? I can solve this system for x, and this x will get me as close as possible to b as any x possibly could. That's cool. All right, but there's another way of thinking about this problem geometrically. That's sort of the recurring theme for this. So let's see, what page of my notes am I on? In order to illustrate this, let's try a simpler example. What's going on geometrically? Ah! That is painful. So we have an overdetermined problem here, which means that I'm not going to be able to take my ingredients, my chocolate milkshake and my French fries, and add some combination that's going to get me where I want to go. In this case, it's a little hard to see because I just picked a random matrix with some funny numbers in it. Let's pick an example that makes the geometry easier to see. So here's an overdetermined system. 1, 2, 3, 1, 0, 0, x equals 5, 3, 6. All right, so can someone convince me quickly that there's clearly no way that I can solve this system exactly?
0 equals 6 in the last line.
Yeah, obviously there's no way I can ever produce any grams of protein, whatever this third column is, because none of the entrees I have available contain any protein. Everybody on board? Geometrically, what does this look like? Well, if we think about the types of meals that I could create, the types of calorie fat things that do exist, they exist in a two-dimensional subspace of this three-dimensional problem. What does that look like? Well, in this case, it's a subspace spanned by the first two components, calories and, let's say, fat. Right? The one I can't get to is protein. So let's draw that. I picked a three-dimensional example, so I'd have a prayer of drawing it. That's right-handed. Actually, you know what? That's not the. I want to draw it another way. Let's draw it this way. Here's x. Here's y. Here's z. And basically, what I'm asking is, how many for what combinations of b can I actually find a solution? Well, anywhere in the xy plane. Right? I can get anywhere I want in the xy plane. I can get you any combination of nutrition at all, provided there's zero in this third direction. Make sense? All right, so in this case, this point here is at 5, 3, 6, somewhere up here, which is way above the xy plane. So when I solve this problem, I already know that I'm not going to be able to do anything about the error in the z direction. So I might as well solve a problem that only considers the components in the x and y direction. Right? So another way of saying this is, can we come up with a change of coordinates such that that after applying this projection, I end up only in the xy plane? Because I know already that I'm not going to be able to satisfy this z constraint. So what sort of projection, how could I project this problem into the two-dimensional space of the plane? Do you guys remember the discussion about projection matrices last time? Right? In this case, we're going to be projecting from a three-dimensional space into a two-dimensional space. So what are the dimensions of that projection matrix going to look like? It's going to be 2 by 3, right? Because I'm going to right multiply my vector, right? And it's got 3 components. So this matrix had better be 3 wide. And I'm projecting it into a two-dimensional space, so it better be 2 rows tall. Can someone give me an example of a matrix that projects from this three-dimensional space into just the xy plane? about how much people weigh and how tall they are. This will be a familiar example to those of you who were in my class this morning. Right, and so in this case, I go out and I say, okay, you're about, oh, I don't know, 5'7", and you weigh, oh, I don't know, 150, I don't know how much you weigh. Oh, good. Did I overshoot it on the weight? Anyway, so he's been working out. Boy, okay, mouth, foot. In this case, we have uncertainty in both the weight direction and in the height direction. And so the way to minimize, to account for that error involves minimizing, adjusting, taking the curve because I'm uncertain about it. Right? In fact, it gets even a little more complicated because I might be much more uncertain about the x-axis than the y-axis. So in fact, the slope that I use here is actually a function of the ratio of the uncertainties between my measurements in the x direction and in the y direction. Everybody see sort of intuitively where I'm getting at? Now for today, forget it. We're just going to minimize the error in the y direction. We'll actually figure out how to handle the other problem next time. Okay, so here we are. Our error function is going to look just like it did before. Oh, and I said model. So what model are we going to use? Well, we're fitting a model that has, with an error straight up and down. Our y equals mx plus b model is a perfectly fine model to use in that case. What are the parameters that we're trying to solve for? The m's and the b's. Right? The m and b determine what line we're talking about. So we want to figure out how to choose m and b such that this line fits as well as possible. Okay, so we've now got our model. We've decided on our error function. What we do now is we start to write down equations that describe the relationship of our data in terms of our model. So for example, let's take our first data point, which is 1, 1. Now what that's saying is at x equals 1, y is 1. So in other words, 1 times m plus b equals 1. Everybody see what I did? Right, I kept my m's and b's, my parameters, and just plugged in where I have my observed data. I can do the same thing at my second data point, which is 2, 2. Let me put this one here. At 2, 2, I'm going to have 2m plus b equals 2. And then 3, 2, I'm going to have 3m plus b equals 2. Everybody clear? All right, in this case, we've got a nice linear system. So the next step is to rewrite this in the form of a matrix vector product. And we want the vector to be the parameters that we're solving for. Because this is a linear algebra review session, you can guess where we're headed is to an ax equals b problem. We want the x vector to be the parameters that we're solving for. So here's what our goal is. We're going to have a vector over here. And we want to fill in these matrices with constants, right? Constant numbers. What do I put in here? Right, I've got 1m and 1b, so it's going to be 1, 1. How about here? 2, 1. 3, 1. Over here? 1, 2, 2. I'm sorry I didn't draw this to scale exactly, but you guys get the idea. I now have an overdetermined ax equals b problem, which we already know how to solve, right? It's overdetermined, so we're going to have to use the set of normal equations. We'll solve the normal equations instead. And we're going to come up with, when we solve for that, we're going to end up with a value of m and b. And I can tell you that indeed the line fits and it has a low error. Most anticlimactic ending of a lecture ever, perhaps. All right, so we're going to stop here. But what I want to have you guys think about abstractly, what if the model I wanted to fit was more complicated? What if it wasn't a line? What if I wanted to fit a parabola? How would I do that? So it's basically the same thing, right? Step one is decide what your model is going to be. Maybe your model will be y equals ax squared plus bx plus c. Maybe that's your model, in which case you've got 3 parameters that you're solving for. Now you're going to do basically the same thing. You're going to write down the equations which relate your data in terms of your model. Right, so now I'm going to end up with things in here. And there might actually be, when I plug in here, I might have to square things because I've got square terms over here. But notice that the only thing that I have to square here are values corresponding to observed data. Right? So if I observed a point that was, let's say, well, x equals 1, y equals 1, what would my equation look like? A times 1 squared plus b times 1 plus c equals 1. Right? And I could do that again for all of my data points. And I juggle things around so that I have a vector containing just the parameters that I want to solve for, and I solve them. So there's an example in the notes, which will be on the website later on. I recommend heartily that you take a look at it and see if you can get the same answer I got. Question?
For the linear version, could you run into problems when you approach vertical lines?
Absolutely. So in this case, y equals mx plus b has the classic problem that it doesn't work if the line is straight up and down. Now, actually, that's not really a problem because our error model also doesn't work if the line is straight up and down because you end up with infinite distances. The more general version, which we'll talk about on Friday, addresses that problem. We'll have a more general representation for the line. All right, thank you very much. Oh, one more question.
You just said we can look at notes.
Yes,
What notes?
the notes that I post on my website. april.eeks.umich.edu/courses. Thanks, everybody. See you on Friday. 6, 5, 4, 3, 2, 1. Oh, pardon me.